take it away.
All right, thank you. So this is an experience report about a language called Plinth. And so I'll preface it by saying that besides my co-authors here, there are many others, perhaps too many to name individually, who have contributed to or influenced Plinth over time. I think there are actually a few in this room. So Plinth is a DSL for writing smart contracts on Cardano, on the Cardano blockchain. So let me first zoom out and tell you, where Plinth sits in the space of DSLs. So broadly speaking, there are three approaches for DSLs, like standalone DSL, which are new languages. And then there's EDSLs, which should require no further introduction to this room because, in the Haskell community, we talk about EDSLs all the time. And then there's also language that are subsets of other general purpose languages. This is a relatively less common approach, but it can sometimes work very well, and Plinth is in this category. So here are some examples, and the examples on the right these are all Cardano smart contracts languages. And so that means, when you learn about Plinth, the takeaways are not just from the angle of how, what it's like to implement this language in Haskell, but there's also the aspect of, how this approach compares to other approaches of developing DSLs. So specifically to motivate Plinth even further, what makes it interesting, right? Why you should care. So there are a number of different things. So Plinth reuses a subset of Haskell, like I just said. And this is a relatively less common approach. There's just not that many DSLs that adopt this approach. And so why did we adopt this approach, you might wonder. And second, so the Plinth compiler is implemented as a GHC plugin. So this is also a less common approach within the already less common group of subsets of other languages. Because a more common approach for implementing a compiler for something like Plinth is to develop a standalone compiler with GHC, using GHC as a library. So it will be interesting to see how these, how they compare and what are the trade-offs. And then the Plinth runtime itself is also a sort of fairly interesting piece of Haskell. It's a performance-optimized Haskell implementation of a CEK machine. And it shows that, it's actually fairly performant and the code is actually fairly high level and readable. So it shows that Haskell as a high level, purely functional language is not like inherently inefficient, and you can indeed write very performance optimized code without really sacrificing readability if you spend some effort on it. So I'll speak to these three things in more details. The other three I won't have time to go into, but I will just briefly mention them at the end. So first, a subset of Haskell. What does it mean to say that Plinth reuses a subset of Haskell? So it means that the code is written directly in Haskell syntax, which is unlike EDSLs, which usually needs to invent its own syntax on top of Haskell's, because EDSLs are just a regular Haskell library for manipulating expressions or ASTs. And users will just need to use whatever types and functions provided by those libraries. And by the way, since this is the Haskell symposium, so when I say EDSL, let's assume that it's embedded in Haskell. And then the code is compiled directly, and this is also so code gets compiled directly by some compiler that is either different from GHC or a modified version of GHC. So this is also unlike EDSLs, which is a regular Haskell library. So all the interesting things, including the compilation of the DSL, happens at Haskell runtime. And this is some of the supported and unsupported features, Haskell features by Plinth. So most of the core FP features are supported, but some of the more advanced features are not. And there are also some semantic differences between Plinth and Haskell. So Plinth is strict, so all the function applications are strict. Bindings, you can have strict or non-strict bindings. You can use tilde patterns to define non-strict bindings, but there's no there's no lazy evaluation in the runtime. So the non-strict bindings are evaluated by name. And this is the first stage, the front end of the Plinth compilation. So we simply just reuse the standard GHC front end. So that shows that indeed Plinth just reuses a subset of Haskell syntax. So like I said before, there are two other approaches for doing DSLs. There are standalone DSLs and there are EDSLs. So standalone DSLs are obviously very different, but I do want to talk a little bit more about EDSLs because they are more similar to Plinth. So again, EDSLs are just regular Haskell libraries for manipulating expressions or ASTs. And that is the case with both deep embedding and shallow embedding. So EDSLs have a few advantages, like they are highly customizable. I mean, not as highly as if you create a new language, but still, like syntax-wise, there may be some constraints, but semantically is quite highly customizable. Like for example, your host language might be a functional language like Haskell, but your EDSL can be an imperative language, right? That's totally fine. There's no problem with that because you can define your language in AST however you like. And it's also relatively easy to develop. Again, it's just a regular Haskell library, so there's nothing super fancy going on here. And you get meta-programming for free because meta-programming is compile-time programming. So your DSL's compile time, your DSL's compile time is just Haskell runtime. So meta-programming for EDSL is just like plain vanilla Haskell. So no TH or anything like that. So it doesn't get any easier than that. But there are some major drawbacks, mainly that it creates some burdens for the users. So users are writing not simple code, but users are writing code manipulating ASTs explicitly. And what that means is, for example, you don't get to use the simple int type. You have to use something like AST of int. And when you need to compare it to ints, normally you don't get to use the operator, the regular operator on the top, and you have to use something like the one on the bottom. Sometimes you can recover some of those regular operators, but only with heavy overloading, which has its own complexity. And limited support for pattern matching or branching, because if you write like if then else in Haskell, or if you do a regular pattern matching in Haskell, that branching occurs at Haskell runtime. But Haskell runtime is your DSL's compile time, so that's the problem. If you want your DSL to support branching or pattern matching at runtime, then you have to come up with your own branching operators, which are usually much more awkward to use than just the simple if then else. Having said that, in Haskell, there is a way to recover some of the nice syntaxes because of this rebindable syntax extension. But that also comes with its own problems. There are also other clever things you can do, in an EDSL to make it as ergonomic as possible. But I'll just read a quote by Kono Elliott. This is from the paper Compiling the Categories. So additional efforts can hide more of these symptoms, but the cracks still show, and each new coping mechanism leads to increasingly mysterious type errors. So that's EDSL. Plinth, by contrast, is like reuses a subset of Haskell. So the good things about Plinth is that it reuses Haskell syntax without any restriction. If you want to use int, you just use int. If you want to compare two ints, you just use the regular comparison operator. And if you want if then else, you just do if then else. Everything is regular Haskell. And because of that, the code is relatively simple and it's relatively easier to learn and adopt. And transferable skills, because when someone perhaps new to Haskell is learning Plinth, they are also essentially learning some basic Haskell, which is a very useful thing to do. I don't need to sell Haskell to this audience, right? I think we probably all agree that learning some basic Haskell is probably one of the best things anyone can do to themselves. Like that, it will make you a better person. It will purify your soul, and it will probably it will probably add 5 years to your life or more, right? So I think we probably all agree with that. But unfortunately, there are also some drawbacks of this approach. First of all, limited applicability, and this is probably why this approach is relatively more niche, is because now your DSL is much more constrained by what your host language is and does. For example, if your host language is Haskell or some functional language, and you want your DSL to be imperative language, then this approach is probably a very bad idea because it's not Haskell anymore. And then deep integration with GHC, because now it's no longer a regular Haskell library, right? You need deep integration with GHC, which is tricky, very tricky, because GHC is not designed to compile Plinth. So I mean, it is somewhat customizable, but not fully customizable, and you really feel like sometimes you're just twisting its arms to make it do things it doesn't want to do. And sometimes I open issues in the GHC repository, and I ask, like, can we make GHC do this or that? And then Simon would reply and be like, why would anyone want to do that? Right? Like so it's tough. But I mean, fortunately, we do have. I do have some coworkers who also have merge permission to GHC, so that's very useful. And semantic difference against Haskell. So this is also a problem. So for example, the lack of lazy evaluation means that some of the idiomatic ways of writing Haskell are not good ways of writing Plinth. It can lead to very inefficient code. But I don't know, maybe that's a good thing, who knows, because Richard just told us in his keynote that he thinks lazy evaluations are confusing, right? So so Plinth has no lazy evaluation whatsoever. That means it's like completely clear, right? So that's Plinth. Yeah, that's a subset Haskell. Now, number two, the second thing I said about what makes Plinth interesting is that the bulk of the compilation happens in the GHC plugin. So here it is. So it translates GHC core to compiled code. So it goes through a PIR, which is Plutus IR, and then typed Plutus core, TPLC, and then UPLC, untyped Plutus core, which is the final target. The core language here that everything else revolves around is typed Plutus core, so TPLC. So it's a system F omega based calculus with iso recursive types. And there are a number of reasons why we use this as our core language. I mean, it aligns well with Cardano's philosophy of predictability and determinism, and it's also grounded in extensive academic research. Right? System F has been around for many years. I mean, as Phil likes to say, how do you know that your language won't be obsolete in 50 years? Well, use one that was invented 50 years ago. Use one that was invented twice, and that was System F. And then, based on TPLC, then came the untyped version, UPLC, which is the final compilation target. And a PIR is a high-level IR, so it extends TPLC with things like bindings, recursive bindings, and recursive data types, which makes it like 10 times more readable and very suitable as a high-level IR. Oops, something happened. All right, here's a concrete example. So on the left, so this is Plinth, and here's a function any less than 10. And as you can see, this is just like plain vanilla, simple, basic Haskell. I think anybody can learn to write this very, very easily. And this is PIR, so this is the first step of the transformation. So PIR, as you can see, is fairly readable. It's basically there's this recursive data type called list, and then there's this basically a recursive function Go that operates on the list. And then, yeah, you have a question?
I see a double bar or there. You said there was no laziness.
Yeah, so the only laziness is the Boolean operators like and or. So it's like most other strict languages. So this is TPLC. TPLC is much significantly less readable. So this is not intended for you to read. because all the nice things are compiled away, right? All the data types, all the recursion, all the bindings are compiled away. And also because of the ISO recursive type, there's a lot of like wrapping, unwrapping, so it's much less readable. And then finally, it gets compiled to UPLC. So this is basically untyped lambda calculus with a bunch of built-in types and functions. So now, an alternative way, as I mentioned earlier, of implementing a compiler for something like Plinth is to implement a standalone compiler using GHC as a library. So what are the trade-offs here? With a standalone compiler, you get a more, it gives you a more first-class feel, right? Because now your language has its own compiler. So you're no longer like reusing GHC to do something it's not designed to do. So more of a first-class feel. Although this point is a bit subjective. And it gives you more control of the pipeline. So now if you are not happy with the GHC parser, you can just strip it and replace it with your own parser, or you can replace part of the parser. But on the flip side, there's less overlap with standard Haskell development. So for a team or a project that's already invested in the Haskell infrastructure, like more of a first-class feel might be a bad thing because now you're introducing additional compiler, additional tooling to your stack, and more importantly, a standalone compiler makes it harder to inspect and manipulate compiled code in Haskell. So in other words, it makes it harder to mix regular Haskell and Plinth together in the same project. And this is a very useful thing to do because oftentimes you want to further manipulate your compiled code at Haskell runtime. Or you may want to test your compiled code using quick check, HashHog, or whatever Haskell test framework. So this is a very useful thing to do. And to that point, this is a very important use case of manipulating compiled code at Haskell runtime is lifting. So I'm not going to go into details here, but lifting so this is very similar to lifting in template Haskell. So if you know how lifting works in TH, then you know how lifting works here. It basically, you're serializing a Haskell runtime value into your AST. And this is very useful for parameterized contracts because there's a parameter, runtime parameter that you want to put in your contract. And the key point is that the plugin approach conveniently allows this, where if you have a standalone compiler, it makes it much more difficult. Okay, so let's move on to the runtime. The UPLC evaluator. So it's a performance-optimized implementation of a CEK machine. And this evaluator lives in the Cardano node. A Cardano node is basically a computer or machine running the Cardano blockchain protocol, right? So inside the node, we have this CEK machine that processes UPLC or Plutus scripts. So UPLC and Plutus are, they mean the same thing. So you submit your Plutus scripts to the node in a transaction, right? So you put it in a transaction, you put, where you specify a Plutus script and your expected cost, and you submit it, and the node validates the transaction. Part of validating the transaction is to run the script. And when running the script, there are a number of possible different outcomes. The happy path is that it succeeds with the actual cost. Or it may fail because perhaps the budget is exceeded, or perhaps some validation condition failed, or perhaps the machine got stuck, which means no transition rule applies, which means your UPLC program is not well typed, which cannot happen if you compile it from Plinth, but it certainly can happen if you compile it from a different surface language because there are a bunch of other languages. Or it can also happen if you write, the UPLC by hand, right? So these are the different outcomes, and then predictability. So here I picture the CEK machine as a slot machine, which it's of course a joke. It's in reality the CEK machine is like the polar opposite of a slot machine. So everything is like completely not just deterministic, but also predictable in the sense that you can, before you submit your transaction, you can test it offline. You can test it off-chain. You can run the CEK machine off-chain, run your script, and if it succeeds off-chain, then it will it's guaranteed to succeed on-chain. So which is a very nice property. But I mean, you might wonder how that is possible, right? Because surely the outcome of executing a script must depend on some kind of blockchain state, right? For example, the current time, or whether you have enough money in your wallet and things like that. So how can you completely predict this? And the very short answer to this is that the outcome of submitting a transaction is not predictable, right? So the transaction may fail because timing constraints are violated, or maybe because there's not enough money in your wallet. But in those cases, the transaction will be rejected immediately without running the script. So the guarantee is that if your script is run, then you will know that it's guaranteed to succeed, which is very nice property because running the script is the most expensive part of validating a transaction. So you don't want to waste any money by running your script on-chain, which you have to pay for, only for it to fail unexpectedly. So this is completely predictable. So here, I just want to flash you some code fragments of the UPLC evaluator. And the point I'm trying to make is that it is quite readable and high level. So there are basically two main functions: compute CK and return CK. So this is compute CK. And as you can see, even though we need to squeeze the maximum performance out of this, the code remains pretty high level, pretty readable, and this is return CK. In fact, I mean the code is so readable that when other people want to implement their own UPLC evaluator CK machine in a different language, they tell us that they often use our Haskell implementation. They often refer to the Haskell implementation as their reference, even though we have a formal spec of the CK machine. And we also have an Agda formalization of the CK machine, but they still prefer to read Haskell. So that goes to show you that Haskell is indeed very well suited for implementing something that demands high performance, like a blockchain VM, without compromising readability. I mean, either that or that our spec is very badly written. But I think it's the former. Now, a little bit more on squeezing out performance. So, these are some of the things we do for squeezing performance, like ban patterns, tilde patterns, inline, no inline, unpack, and things like that. So these are, of course, not trivial because in different places you want opposite things. Sometimes you want ban, sometimes you want tilde, sometimes you want inline, sometimes you want no inline. So it's not trivial, but the good thing is that these things they are mostly just like pragmas or things like that. They don't really compromise readability. So your performance optimized code remains fairly readable, and I think this is a great strength of Haskell. But the process is far from trivial. It involves lots and lots of reading GHC core, because that's the only way to reliably know whether GHC does the things you want it to do. I think Richard also touched on this point in his keynotes, is that optimizations in GHC is more like black magic, right? So sometimes you add an inline pragma, but for some reason GHC refuses to inline it. And sometimes an optimization may fire for one piece of code, but it may not fire for another very similar piece of code. Or sometimes things may change if you put a function in a different module, or if you export different things from a module. So it's very subtle. The only way to know for sure is to read GHC core, which is something we spend a lot of time doing. But fortunately, I mean, GHC core is fairly readable. Like I think among all the IRs used by all the compilers, I think GHC core is like fairly easy on the eyes. I mean, it's not even that different from the surface language. So lots of reading GHC core. So this future work, I think arguably the most important thing right now is the first one, which is more front-end customization, because like I said earlier, we are right now just using the standard GHC front-end with no customization, and that creates a number of problems. And I think more front-end customization will let us do things like catching unsupported Haskell features earlier and generating better error messages and things like that. And then other architecture options we'd like to explore, including the standalone compiler option that I mentioned earlier, and or maybe going the other direction, which is even tighter integration with GHC. How about maybe making the Plinth compiler a dedicated GHC backend, like the JS backend or Wasm backend. So that's an idea. And language features like laziness and modules, these are also very useful. So for modules, actually, there's a very lengthy and very detailed, very nicely written proposal about this, written by John Hughes. And it's actually quite fun to read. For laziness, we don't have much idea right now, but I don't know if John wants to write another proposal or not, but I guess we'll see. So let's get back to what makes Plinth interesting. So I talked about the first three. Let me just briefly mention the other three. So compiler optimizations would be, it's interesting to look into Plinth's compiler optimizations, especially in contrast with GHCs, because even though Plinth reuses a subset of Haskell, the different use cases and different runtime requires very different optimization choices, and this could offer some useful insights if you're developing a somewhat similar language. And compiling data types, so there are three ways that to encode data types in UPLC and with different trade-offs. And these are also implemented in very different ways. So there are some interesting stuff there. And the need to predict execution cost accurately is perhaps a unique challenge for a blockchain language. And that certainly put a limit on what we can do and what kind of language features we can offer. So more details about these are available in the paper or in the repository. So let me just end by saying that what Plinth shows is, I hope, not just how a particular language can be implemented in a particular way, but also a demonstration that Haskell is very well suited, if not particularly well suited for powering a global scale system like a blockchain, which millions of people use and rely on. And so, as the Haskell community, I hope we can, continue building upon these ideas and take them further and, continue to demonstrate the value of Haskell in the years to come. And these are links to some of the things I mentioned earlier. And thank you very much for your time.
So thank you for the talk. So when you compare the different approaches of doing DSLs, I think apart from all of the other considerations, one of the key factors that you actually had a successful story is that you had a team which is highly has great expertise in GHC development and is tightly integrated into that GHC developers community. So is that a takeaway for me is that don't ever try this approach if you don't have that team?
Yeah, exactly. So Plinth is particularly attractive to teams that are already invested in Haskell infrastructure and Haskell knowledge. And unfortunately, that's probably why Plinth is not the most popular Cardano smart contract language right now, because such teams are rare. So Haskell is relatively niche, which doesn't really help.
Let's thank the speaker again.
Thank you.